Hello guys, in the previous video we saw that how to calculate the area of a boundary region by using rectangles. At that time we said all the rectangles they have the same width, they have the same base, and the height of each rectangle is determined by either left endpoint method or right endpoint method, right? Okay. What if the rectangles we're choosing they have different base and the height is determined by a random x value in each subinterval. Now, in this case, can we still guarantee that we are able to use those rectangles to find the area of the boundary region? Okay, the answer to this question is yes. If the function y equals fx satisfy a certain condition. Now, in this video, I will show you what is that condition, and if function satisfies that condition, which method should we use to find the area of this boundary region. Okay, so let's say this problem. Here we have a graph of some function y equals fx. And you can see when I construct my rectangles, I'm using the rectangles with a different base, right? So this one, the first rectangle, the base is this, and for the second rectangle, the base is shorter than the first one, right? Okay, so this is one thing. Now the second thing, how I construct the height of each rectangle. Like here, for the first rectangle, I think I'm using the right endpoint method. So the height of the first rectangle equals the function value at this point. Now for the second rectangle, I'm not using neither the left point nor the right point. I'm using a random point between them. So the function value at this point equals this, right? So my second rectangle, the height is equals to this number. That's why it looks like this. Okay. And the third rectangle, the height is determined by the function value at this point. Okay. Okay. So because the width of each rectangle is different, now the delta x is not a constant. Then how do we represent the width of each rectangle? We introduce another notation. We call it delta x sub k. So what is a delta x sub k? Delta x sub k is the difference between x sub k and x sub k minus 1. Like we said, the first point A, we let be x0, and the next point will be x1. So the width of the first rectangle is the difference between x1 and x0, and this difference we use this notation delta x sub 1 to represent. So delta x sub k will be the length of the kth subinterval. Like here we have x k minus 1 and xk. So the length of this subinterval we call it delta x sub k. Okay. Therefore, the area of the kth rectangle gonna be equal to the function value of a random point on the kth subinterval. So I call that point xk star. And so this gonna give us the height. And the width is the length of the kth subinterval, which is delta xk. Okay, like the area of the first rectangle is f of x1 star and times delta x1. So x1 star is a random point on the first subinterval. Now this point, it can be A, it can be x1, and it can be any point between A and x1. Now, if we add up them together, let's say I construct n rectangles and I add up them together, that summation in mathematics is called a Riemann sum. Okay, so here is a definition of a Riemann sum. It says let fx be defined on the closed interval from A to B, and suppose that this closed interval AB is divided into n subintervals, x0 from x1, x1 from x2, all the way to xn minus 1 to xn, with delta xk is the width of the kth subinterval. And if we let xk star be a point in the kth subinterval, so this is a random point on the kth subinterval. So it can be any point between these two numbers, or it can be one of these two numbers. Okay. Then this summation f of xk star times delta xk, which is f of x1 star times delta x1 plus f of x2 star times delta x2 plus all the way f of xn star times delta xn is called a Riemann sum. Okay. Now, if we take the limit of this Riemann sum as this symbol approaches 0. Now, what does this symbol mean is this is read as the norm of delta. So what does this mean is the max or this is the largest length of the subinterval. So this stands for the largest length of one of these subintervals. So of course, if the largest length of the subinterval goes to 0, then the length of other subintervals will all go to 0. Okay, and if this limit exists, then we say the function fx is integrable on AB on this closed interval, and this limit, the limit of this Riemann sum, we can represent it by using this symbol, and this symbol is called the definite integral of the function fx from A to B. So So what this means is if the limit of this Riemann sum exists, then as we learned in the previous video, this limit will give us the area, exact area of this bound region. Therefore, the area of this bound region, now we can use this symbol, this definite integral, to represent. So in this notation, A and B, they stands for these two bonds, x equals A and x equals B, and fx stands for the function of this curve. Okay. Now remember, I said this is not always true unless the function fx satisfies a certain condition, right? So what is that condition? That condition is the function must be continuous on the closed interval. So so here we have this theorem. If a function fx is continuous on the closed interval ab, then fx is integrable on ab, and that means the limit, if a function is integrable, then this limit exists. And if this limit exists, this definite integral will exist. Okay, then let's look at what's the difference between a definite integral and an indefinite integral. Now, indefinite integral we learned in the previous lectures, right? We said the result of an indefinite integral is a family of antiderivatives, like this is an indefinite integral, and the result equals x to the third over 3 plus a constant. This is a family of antiderivative of this function, x squared. And the answer, the result of a definite integral, is a number. Why is number? Because the result of a definite integral gave us the area of a boundary region. So that's why it is a number.